Welcome back to our course, Fundamentals of Operating Systems, based on the textbook Operating System Concepts, 10th edition, by Silbershatz, Gagne, and Galvin. We are working on the 13th unit of our course. This topic is the file system management portion of the operating system. We've just completed lesson 1 in this unit, and now let's proceed to lesson 2. As we've already mentioned, most of the file operations involve searching the directory for the entry associated with the named file. To avoid this constant searching, many systems require that an open system call be made before the file is first used, as we discussed in the last lesson. The operating system keeps a table called the Open File Table, containing information about all open files. When a file operation is requested, the file is specified via an index into this table, so no searching is required. When the file is no longer being actively used, it is closed by the process and the operating system removes its entry from the open file table, potentially releasing locks. Create and delete are system calls that work with closed rather than open files. Some systems implicitly open a file when the first reference to it is made. The file is automatically closed when the job or program that opened the file terminates. Most systems require that the programmer open a file explicitly with the open system call before that file can be used. The open operation takes a file name and searches the directory, copying the directory entry into the open file table. The open call can also accept access mode information, things like create, read only, read write, append only, and so on. This mode is checked against the file's permissions. If the requested mode is allowed, the file is open for the process. The open system call typically returns a pointer to the entry in the open file table. This pointer, not the actual file name, is used in all input-output operations, avoiding any further searching and simplifying the system call interface. The implementation of the open and close operations is much more complicated in an environment where several processes may open the file simultaneously. This may occur in a system where several different applications open the same file at the same time. Typically, the operating system uses two levels of internal tables, a per process table and a system-wide table. The per process table tracks all files that a process has open. Stored in this table is information regarding the process's use of the file. For example, the current file pointer for each file is found here. Access rights to the file and the file accounting information can also be included. Each entry in the per process table in turn points to a system-wide open file table. The system-wide table contains process-independent information, such as the location of the file on the disk, access dates, and file size. Once a file has been opened by one process, the system-wide table includes an entry for the file. When another process executes an open call, a new entry is simply added to the process's open file table, pointing to the appropriate entry in the system-wide table. Typically, the open file table also has an open count associated with each file to indicate how many processes have the file open. Each close decreases this open count, and when the open count reaches 0, the file is no longer in use and the file's entry is removed from the open file table. So, in summary, several pieces of information are associated with an open file. There's the file pointer. On systems that do not include a file offset as part of the read and write system calls, the system must track the last read-write location as a current file position pointer. This pointer is unique to each process operating on the file and therefore must be kept separate from the on-disk file attributes. Also, there's the file open count. As files are closed, the operating system must reuse its open file table entries or it could run out of space in the table. Multiple processes may have opened a file, and the system must wait for the last file to close before removing the open file table entry. The file open count tracks the number of opens and closes and reaches 0 on the last closed. The system can then remove the entry. In addition, there's the location of the file. Most file operations require the system to read or write data within the file. The information needed to locate the file, wherever it is located, be it on mass storage, on a file server across a network, or even on a RAM drive, is kept in memory so that the system does not have to read it from the directory structure for each operation. Finally, there's access rights. Each process opens a file in an access mode. This information is stored on the per process table so the operating system can allow or deny subsequent input-output requests. Some operating systems provide facilities for locking an open file or sections of a file. These should remind us of the unit we covered on synchronization, remember? File locks allow one process to lock a file and prevent other processes from gaining access to it. File locks are useful for files that are shared by several processes. For example, a system log file can be accessed and modified by a number of processes in the system. A shared lock is like a reader lock in that several processes can acquire the lock concurrently. On the other hand, an exclusive lock behaves like a writer lock. Only one process at a time can acquire such a lock. It's important to note that not all operating systems provide both types of locks. Some systems provide only exclusive file locking. Furthermore, operating systems may provide either mandatory or advisory file locking mechanisms. With mandatory locking, once a process acquires an exclusive lock, the operating system will prevent any other process from accessing the locked file. For example, assume a process acquires an exclusive lock on a file system log. If we attempt to open system.log from another process, for example a text editor, the operating system will prevent access until the exclusive lock is released. Alternatively, if the lock is advisory, then the operating system will not prevent the text editor from acquiring access to system.log. Rather, the text editor must be written so that it manually acquires the lock before accessing the file. In other words, if the locking scheme is mandatory, the operating system ensures locking integrity. For advisory locking, it is up to the software developers to ensure that locks are appropriately required and released. As a general rule, Windows operating systems adopt mandatory locking and Unix systems employ advisory locks. The use of file locks requires the same precautions as ordinary process synchronization. For example, programmers developing on systems with mandatory locking must be careful to hold exclusive file locks only while they're accessing the file. Otherwise, they will prevent other processes from accessing the file as well. Furthermore, some measures must be taken to ensure that two or more processes do not become involved in a deadlock while trying to acquire locks. When we design a file system, we always consider whether the operating system should recognize and support file types. If an operating system recognizes a file type, it can then operate on the file in reasonable ways. How often have you selected a file from a list to find that the operating system knew to open Microsoft Word, Excel, or whatever to read it? A common mistake occurs when a user tries to output the binary object form of a program. This attempt normally produces garbage. However, the attempt can succeed if the operating system has been told that the file is a binary object program. A common technique for implementing file types is to include the type as part of the file name. The name is split into two parts, a name and an extension, usually separated by a period as shown in this figure. In this way, the user and the operating system can tell from the name alone what the type of the file is. Most operating systems allow users to specify a file name as a sequence of characters followed by a period and terminated with an extension made up of additional characters. Examples include resume.docx, server.c, which would be a C file, redthreader.cpp. This is a characteristic of the Windows operating system, but it is not Unix. The system uses the extension to indicate the type of file and the type of operations that can be done on that file. Only a file with a .com, .exe, or .sh extension can be executed, for example. Well, that's actually not true. You and I created a .bat file at the beginning of the course, remember? And that can be executed, but that's very much like a .sh file. The .com and the .exe files are two forms of binary executable files, whereas the .sh file is a shell script containing, in ASCII format, commands to the operating system, just like we did with that .bat file earlier in the course. Application programs also use extensions to indicate the file types in which they're interested. For example, Java compilers expect source files to have a .java extension, and the Microsoft Word word processor expects its files to end with .doc or .docx extension. These extensions are not always required, so a user may specify a file without the extension to save typing, and the application will look for a file with the given name and the extension it expects. Because these extensions are not supported by the operating system, they could be considered hints to the applications that operate on them. Consider, too, the Mac OS operating system. In this system, each file has a type such as .app for application. Each file also has a creator attribute containing the name of the program that created it. This attribute is set by the operating system during the create system call, so its use is enforced and supported by the system. For example, a file produced by a word processor has the word processor's name as its creator. When the user opens that file, By double-clicking the mouse on the icon representing the file, the word processor is automatically invoked. The file is loaded, ready to be edited, just as I mentioned a moment ago. The Unix system uses a special number stored at the beginning of some binary files to indicate the type of data in the file, for example, the format for an image file. Likewise, it uses a text special number at the start of text files to indicate the type of file, which shell language a script is written in, and so on. Not all files have special numbers, so system features cannot be based solely on this information. Unix does not record the name of the creating program either. Unix does allow file name extension hints, but these extensions are neither enforced nor depended on by the operating system. They are meant mostly just to help the users in determining what type of context the file contains. Extensions can be used or ignored by a given application, but that is up to the application's programmer. File types can also be used to indicate the internal structure of the file. Source and object files have structures that match the expectations of the programs that read them. Further, certain files must conform to a required structure that is understood by the operating system. For example, the operating system requires that an executable file have a specific structure so that it can determine where in memory to load the file and what the location of the first instruction is. Some operating systems extend this idea into a set of system-supported file structures, with sets of special operations for manipulating files with those structures. This point brings us to one of the disadvantages of having the operating system support multiple file structures. It makes the operating system large and cumbersome. If the operating system defines 5 different file structures, it needs to contain the code to support those file structures. In addition, it may be necessary to define every file as one of the file types supported by the operating system. When new applications require information structured in ways not supported by the operating systems, severe problems can occur. For example, assume that a system supports 2 file types: text files, composed of ASCII characters separated by a carriage return and a line feed, and executable binary files. Now, if we, as users, want to define an encrypted file to protect the contents from being read by unauthorized people, we may find neither file type to be appropriate. The encrypted file is not ASCII text lines, but rather is apparently random bits. Although it may appear to be a binary file, it is not executable. As a result, we may have to circumvent or misuse the operating system's file type mechanism or abandon our encryption scheme. Some operating systems impose and support a minimal number of file structures. This approach has been adopted by Unix and Windows and others. Unix considers each file a sequence of 8-bit bytes. No interpretation of these bits is made by the operating system. This scheme provides maximum flexibility, but very little support. Each application program must include its own code to interpret the input file as to the appropriate structure. However, all operating systems must support at least one structure, that is the executable file, so that the system is able to load and run programs. There are common file types as shown in this graphic. You see all these that end with the extension of .exe, .com, and so on. These are executable files. Format.com is an example, a file that can be very dangerous if improperly used. Certain types of objects like .obj and so forth are compiled in machine language but not linked to anything. source code. That's .c. If you say format .c, what you're describing there is the source code for a C language program. .cc, .java, and so on. .bat, as you and I learned earlier in the course, is a batch file, and .sh is a shell file. .text is a text file, pure and simple. You can use Notepad to open that. .doc is a common extension for Microsoft Word and by default a number of other word processing systems. .wp, .doc, and so forth are various word processing files. .lib, .dll, these are libraries. .jpeg, .ps, PostScript, .pdf, .jpg are image files, binary image files. .arc, .zip, .tar are all archive files. These are files that are used to combine a number of files to be transported, for example. And then there's multimedia files like the .mpg, .mov, and so on. These are the various file types that you will find quite often. Well, I'm afraid I let that one get away from me a little bit, and it resulted in a video that is much longer than I prefer. But so let's take a break here, take your time, go back and review your notes, update your study guide. And when you come back, I believe we will be finishing our course with the next lesson on the file system management of the operating system.